Hello, my name is Jemariah Valencia and I'm from Lab Section MO4. This is my Lab 5 Part 1 Motion of Falling Objects Video Lab Report. And my observation includes a green apple and a ball of sock falling from a high place. And my main result is that by using physics concepts, the computer models predicted the positioning of the falling objects. And I made two models for each object, one with only the force of gravity and another with the force of drag and gravity. So this is my apple. I'll first do the apple, and I oriented my axis so that it is falling in the negative y direction, and I also calibrated my stick to the diameter of the apple, which is 0.07 meters. And as for the position of the apple, or the position that I tracked, I put it at the center of the apple, which is the point of mass for this tracker. And also I oriented it so that the origin is the initial position, and also since the criteria was it was at rest, the initial velocity is also 0. And as you can see, the ball is falling, and as time increases, the negative y positioning also decreases. And I then took this information and put it in the spreadsheet and made a graph. But before I show you the graph, I will show you the coding for this, and I used the initial position of 0, 0, which is the origin, and the initial velocity, which is 0, as rest, and the time step as 0.033 as seen in the tracker. The total time of this was 1.33, and so I also used that as the total time for this computational model. And since the first one, I will show you the one that has no drag force yet, and so the B value will be 0. And this is the model running, and it looks similar to the tracker, but later on I will show you that it is much different because of the drag force. And after trying to make the model look like the experiment, I found that the B value for this apple was 0.0972, and you will see that it'll look similar, but as you can see, it looks similar as the other two graphs. But as I compare them in the spreadsheet, you can see that the experiment, the orange dot, and the blue line, which is the model with the drag, is very, very close, and it's almost identical. Meanwhile, the gray line, which is the model without the drag, is kind of far away. So meaning that the apple was falling with the gravity and the drag force acting upon it. And the drag force is related to gravity, as in that if they start to equal each other, the force of net will equal to 0, and that's when the object reaches terminal velocity. And I will talk more about that later on. The relationship between the drag and the velocity is also seen in this model, in this coding, in that the B value, the value that I figured out, multiplied by the magnitude of the velocity times the vector equals the force of drag. So as the ball velocity increases, the force of drag also increases. I then did the exact same thing with the sock, and I oriented my axis the same way with the negative y where it is falling, and also I started my initial position in the origin. And as you can see, the center of the point of mass is also the center of the sock ball, and I calibrated my stick to 0.008 because that is the diameter of the sock ball. I also ended right before the ball hit the ground, and I took this information and I put them in the model, the initial conditions of 0, 0 origin, and the 0 or rest velocity, and the time step is the same, but this time the time was 1.733 because that is the whole duration of the sock falling. And so as I run this, it'll look similar to what the graph of the tracker looked like, but also similar with the apple. I can't only take the gravity into account, so in order to get the force net, I also tried to figure out the B value so that the drag force can act onto the computational model and it'll look like the experiment. And so I found the B value to be 0.00346, and when I run this, it'll look like this. The graph will look similar to the tracker and the first model with only the gravity, but as you see in this graph, the orange is this experiment, the blue line is the model with the drag, and the gray line is without the drag. So the predicting the drag force wasn't the same as the apple experiment in that it's not as close to the actual experiment, but it ends in the same point. And so even though it wasn't like the apple experiment, it still predicted very closely. And now I'll answer the what does it mean? For the object that drops slowly, which is my sock, examine the velocity versus time predicted by the models, with and without drag, and predict the terminal velocity. Okay, so in order to get information about the velocity, I changed this to plot the velocity without drag and with drag. So I'll just run it without drag. And so I took this information and I also put that in the Excel sheet. And so velocity versus time. So this is for the sock. The orange is with the drag and the blue is without drag, and this is velocity versus time. As you can see here, the slope begins to straighten out with the drag, and basically this is saying that it is approaching a terminal velocity. When the slope starts to reach the 1, or when there's constant slope, then it reaches terminal velocity, and terminal velocity means that the drag force equals gravity, and this is why it is the computational model with the drag. And so because of the drag force equaling gravity, the force net begins to equal to 0, and basically this equation right here comes force net equals 0, and in turn, when this becomes 0, this whole section right here becomes 0, and the ball velocity would be constant. And this is very close to a constant velocity, but it still shifts a little bit, so it means that my sock didn't really reach a terminal velocity. The next question. The object that drops slowly, which is in my sock. Using models, so I just talked about terminal velocity, and it did not reach terminal velocity. Now compare the terminal velocity in this case with the case where the object is dropped from rest. if there is an initial velocity, the terminal velocity will not change for the same object. So for my sock, it'll have the same terminal velocity. However, only the thing that changes is the time to reach the terminal velocity. So if it starts with initial velocity of something, no matter what that object is, that object will always end up with the same